Good afternoon. Now this is the video number 5 on stiffness matrix, and this is example number 4. Now this continuous beam, we will see the analysis by using a stiffness matrix method. So as compared to the previous example, what the change in this continuous beam are? So the first of all, so the beam support is sink by 10 millimeter. That is the first thing. Next, there is a O rank of of a portion D to A, and it is subjected to UDL. And next is again there is a variation in moment of inertia. So span BC is moment of inertia 3I, and remaining spans is moment of inertia, or moment of inertia is equals to I. Then EI value is given as a 20,000 kilonewton per meter square. Then in the stiffness matrix method, as we discussed in the previous videos, so there are, first of all, we have to generate the 3 matrices. First of all, we'll generate the displacement matrix, then we'll generate the load matrix, and number 3 will generate the stiffness matrix. First of all, the displacement matrix. Now to generate displacement matrix, first of all, determine its degree of freedom. So to calculate the degree of freedom, consider only a structure having the support and show the supports only. So support C is a fixed support. This is fixed support whose degree of freedom is equals to 0. So this is a hinge support. So hinge support, at hinge support only the rotation is possible. So therefore only one degree of freedom, that is a rotational degree of freedom. Similarly, this is also hinge support at which only rotational displacement is possible. So here this is also a rotational degree of freedom. So in all, there are 2 degrees of freedom of the complete structure of a continuous beam. Then give the assign the numbers to this degree of freedom. So we'll call this degree of freedom as a 1. So this degree of freedom is a rotation displacement, that is theta A. Is an unknown displacement at support A. We will call, or will assign this degree of freedom as a number 1, and degree of freedom as at B. So that is theta B, we will assign the number as a 2. Then we can write the displacement matrix as, so there will be 2 elements, 1 column, 2 elements. So here this is the first element. So the first element is the rotational degree of freedom at coordinate 1. So this is a coordinate 1. So what is the rotational degree of freedom here is a theta A. Okay, unknown displacement at coordinate 1 is theta A. Similarly, this is a coordinate displacement, that is element number 2 at coordinate 2. So this is a unknown displacement at coordinate 2. So it is a theta B. So call this equation number 1. So first displacement matrix part is over. Then go for the next the matrix. It is called as a load matrix. Now to calculate the load matrix, calculate the fixed end moments, restraining moments at the ends of the span due to the loading. Now here there are 2 parts. Restraining moments are because of 2. First is the restraining moments because of the sinking of the support. Support B sink by 10 millimeter. Because of that, some restraining moments will develop at the end. And second, additionally, because of the gravity loading, there is a there will be the end moments at the ends. Okay. Now first of all, due to the gravity loading. Okay. So what are the gravity loading? So here this is a DA and AB. This is subjected to UDL of 25 kilonewton per meter. So to calculate the fixed moments, we know that it is required to assume each span as a separate fixed beam. Okay, so AB as a separate fixed beam and subjected to UDL. Okay, and on BC there is no load. On BC there is no external load is there. So therefore fixed moments in BC portion will be equal to 0. In AB portion, so fixed beam subjected to UDL. So it will be WL square by 12. So W value is known, span is known. So calculate the fixed moments. So it will be hogging anti-clockwise direction. This will be clockwise direction. Again, this will be WL square by 12. WL square by 12 in a clockwise direction. So this is for AB portion, and DA portion. So here there is a fixity here. Okay, and this D is a free end, and there is a O rank on this portion. So for for DA portion, just like a cantilever. And because of this loading, okay, this load creates a anti-clockwise movement about support A, and therefore the restraining moment at A will be clockwise. Okay, and how much movement will be equal to? This is 25. 25 is the intensity of the loading. 25 into 2, length is 2. So 25 into 2 into 1. So 25 into 2, it is a 50. So magnitude of this moment will be equal to 50. So these are the end moments due to the external loading. Now, because of the sinking of the support now support B sinks by 10 millimeter. So again, consider each span as a fixed beam. So this is A support, which is at the original level, B support at the lower level. So this is sink by 10 millimeter. So for AB portion, B at a lower level. So therefore, the support which is at a lower level, at that support, there will be a sagging moment will develop. There will be sagging moment develop. So what is the value of this? It will be equal to 6 EI delta upon L square. Okay, so all the values are given. Take all the values in 1 unit, preferably kilonewton meter. So for this case, it will be 6 EI value is 20,000 into delta is given in 10 millimeter. So 10 divided by 1000 in meter divided by span. Okay, span square L square will be the magnitude of this moment in a sagging nature. And at A support, it will be again in the same sense, anti-clockwise. This is also anti-clockwise, but acting from the bottom. Okay, so it will be again 6 EI delta upon L square. Its value is again 75. So this is for AB span. Then for BC span, C is at the original level and B is at a lower level. The support which is at a lower level, so their sinking moment will be sagging nature. So it will be clockwise, and here also clockwise. At the support C, it will be clockwise. And again, what is value? 6 EI delta upon L square. Okay, so delta is 10 millimeter, convert into meter, EI 20,000, and span, what is the span of the BC? Will be the sinking moment for portion BC. Now we can write the load matrix. So load matrix, so again there will be two elements. Size of the matrix will be equal to 2 by 1. Okay, now the first element will be the restraining moment at coordinate 1. Coordinate 1 is our A support. Okay, so here due to loading, this will be the all restraining moment at A support, and this is the restraining moment at A support due to level difference. So use plus sign for clockwise rotation. So this is a plus 50, minus 33.33, and minus 75. So total at coordinate 1, restraining moment will be minus 58.33. Then second element will be restraining moment at coordinate second. Coordinate second is at B point. So at B point, due to loading, these are the restraining moment. So it is a plus 33.33, and this is the restraining moment due to the level difference. So again, this will be a addition of this. So it is a again minus 75, and plus 100, plus 100. Okay, so these are the two movements. Take the just addition. Clockwise rotation positive, anti-clockwise rotation negative. So this will be the second element at coordinate 2, and call this matrix as a 2, equation number 2. Then we'll generate the third matrix, what is called as a stiffness matrix. Okay, now to generate stiffness matrix for this particular structure, so there are two coordinates, therefore size of the matrix will be again 2 by 2. In all, there will be 4 number of elements in the matrix. Now we'll generate the first column of the stiffness matrix. So write the line properly. To generate the first column of the stiffness matrix, apply unit deformation at coordinate 1. Okay, now this is support A, support B, and support C. First of all, provide fixity. First of all, provide restraint at this particular point, and this is the free end. So free end keep as it is, as a free only. Then apply unit deformation at coordinate 1. Now this is our coordinate 1. What is coordinate 1? Coordinate 1 is the rotation. Okay, coordinate 1 is the rotational force. So at coordinate 1, at A, apply the moment. Apply the moment, and how much moment to be applied, so that the slope at A will be equal to 1. Okay. Now, when the moment is applied at support A, how the span will deform? Okay, now on AB portion, the moment is acting from the top, therefore this will deform downward. While as the same moment, if it is continued, then this moment is acting from the bottom on AD portion. And since this is a free end, so therefore this will be lift like this. So this will be deformation in both the part. Okay. Now due to application of this unit deformation, some internal forces will be induced at the ends of the member. Internal, that is movements as well as the reactions. Now for this particular AB part, from this to this, the moment is acting from the top. Okay, then this slope will be equal to 1. This slope will be equal to 1. Now to produce this slope will equal to 1, how much moment is required to apply? How much moment it is? 4 EI by L. Okay, so here it is 4 EI by, and span equal to 4 meter. And how much moment will produce at the far end? It will be equal to half of this. So it will be equal to 2 EI divided by 4. This is for AB portion. Okay, this is for AB portion. Now for A to D portion, since there is this is a what is called as a, here it is a free end is there. So therefore no restraining moment will be produced. Only it will be for AB part. Then and next is BC part remain as it is, because there will not be any effect on BC part. Then the first element K11. Okay, so that is, what is K11? Stiffness at 1 due to unit deformation at 1. Stiffness at 1 due to unit deformation at 1. Now stiffness at 1, in the sense our coordinate 1 is a rotational force. So what is a rotational force at coordinate 1? So how much rotational force it is? 4 EI by 4. Now it is clockwise, and assigned coordinate number 1 is also clockwise. Therefore it will be positive. So 4 EI by 4. So it will be only EI, and EI value is given as a 20,000. So this is the first element. Second element is K21, that is stiffness at coordinate 2. Now coordinate 2 is B point. Coordinate 2 is a B point. So our coordinate 2 is a rotational force. So how much force developed at coordinate 2? It will be equal to 2 EI by 4. It is positive. It is positive. Why positive? Because the force produced here is a clockwise, and our assigned coordinate 2 is also clockwise. So it is in the same sense. Therefore, element will be positive. So it will be equals to 0.5 into 20,000. So this element is 10,000. So these are the two elements in the first column. Then we'll generate the second column of the stiffness matrix. And now to generate the second column of the stiffness matrix, apply unit deformation at coordinate 2. Now the coordinate 2 is at a B point. Now this is our coordinate 2 is a rotational force, that is the moment is there. So apply the moment here. Then how the span will deform? So BC portion, it will deform downward, and AB portion, the moment is acting from the bottom, so it will be hog in the upward direction. So this will be deformation. And this, how much moment to be applied? How much moment to be applied? So this moment to be applied so that the slope at B point will be equal to 1. Then for BC portion, moment of inertia is 3I, and for AB portion, it is only I. Then draw the free body diagram to calculate the end moments. Okay, so now for the AB portion, the moment is in the clockwise direction, so it will be going to hog upward. Then here, how much moment to be applied? This slope will be equal to 1. Now to produce this slope equal to 1, how much moment is required to apply at this point? So it will be equal to 4 EI by 4. Then how much moment will produce at the far end? In the same sense, if it is clockwise, this also clockwise. Half of this, it will be equal to 2 EI by 4. Okay, so this will be, these are the end moments developed at the ends. for AB portion. Similarly for BC portion now. For BC portion, this is a on BC portion, apply clockwise movement. So this will deform downward. Then the slope at this point will be equal to 1. Then how much this movement is required to apply so that the slope will be equal to 1. So it will be equal to 4 EI by span 6, 4 EI by L. And at the far end, it will be in the same sense, it will be equal to 2 EI by 6. Then the second column, now the first element, K12, stiffness at 1. So at coordinate 1, what is the force, rotational force at coordinate 1? How much it is? It is plus, because it is clockwise. Moment produced is clockwise, and our coordinate 1 is also clockwise. So it is 2 EI by L. So 2 EI by L. So it is 0.5 into 20,000. So it is 10,000. Then K22. Okay, so this is coordinate 2. So here both moments produced are clockwise, and therefore both elements will be positive. So this is 4 EI by 4. This is for first element, and this is for second element, for which EI value is equals to 3 EI. Then in the next case, substitute EI equal to 20,000. So answer of this is coming as a 60,000. Okay, so this is the second column of the stiffness matrix, and call this equation number 3. Then we have generated the 3 matrices, then connect it by equilibrium equations. Equilibrium equation is P matrix plus K matrix into delta matrix equal to 0. So this is load matrix from equation number 2. This is a stiffness matrix from equation number 3, and this is the displacement matrix from equation number 1. Then this equation is in the matrix form. Then do the multiplication and write the 2 simultaneous equation. Generate the 2 simultaneous equation. So do the multiplication. 20,000 into theta A plus 10,000 into theta B is equals to, now take this 58.33 on the right side, it becomes plus 58.33. Then second equation is 10,000 into theta A plus 60,000 into theta B is equals to minus 58.34. Equation number. These are the 2 simultaneous equations. So solve this equation and find out the answer of theta A and theta B. So these are the 2 answers of the unknown displacement at support A and support B. One answer is positive, that means this slope is clockwise, and the second theta B is a negative. It means that our assumption regarding the rotation at B, it is wrong. Initially we have assumed, just I will repeat, because in the previous example also I was explained about the signs of theta A, theta B. So here this is the unknown number 1 theta A. We have assumed this as a clockwise. This is theta B. Theta B also we have assumed as a clockwise. Okay, so because here at this stage both are unknowns. So regarding directions, it was not clear whether it is a clockwise or anti-clockwise. Therefore, assumption made. Now, after solving this thing, after determining the answer, now it is clear that one answer is positive. That means this assumption is correct. Okay, so this slope is clockwise and this slope is anti-clockwise. Then use a slope deflection equation after this and find out the final end moments. So these are the slope deflection equation. So for BA part, which is a overhanging portion, so we can use the modified slope deflection equation. So using modified slope deflection, we get MBA equal to 38 sagging nature. Then for BC part, use a general slope deflection equation. So this is general slope deflection equation for BC and for CB. And then plot the bending moment diagram. So this is the end of this example. Thank you.